Hello everyone, my name is Mark. Welcome to my Calc 3 videos. And today we're going to talk about double integrals in rectangular regions. So to start with, I would like to recall some of your memories about single variable integrals. So graphically, what does the integral of a single variable function mean, right? I think your calculus teachers have taught you this before, right? It's the integral of a single variable function is graphically an area under the curve, right? So area under the curve. So area is a two-dimensional object, right? So then what is the next? What if I add another dimension of length to area, right? What do I get, right? If you have area times a length, you can think of it as a height, we probably get a volume, right? So then what does the integral of a two-variable function mean, right? So so for an for integral of a two-variable function, right, if the integrand is 1, we would get the area under the region that we're integrating. But if the integrand is anything else, for example, it's a height of a function at a certain location, then we would be multiplying the height by the area. So then graphically the integral of a two variable function means it's volume under the region. Okay, so for example, right, let z equals to function of x, f(x) and y equals to 1, and then what is the physical meaning of this function, right? So as we have discussed before, if this equals to 1, if the integrand equals to 1, one integral, think about integral as of adding a dimension, okay? Right, so in this case we're adding a dimension of length because x is length, and then derivatives, right, it's the opposite, which is removing a dimension. So the physical meaning is 1 times length times another length, which will give us area, right? And then, but if we have z of fxy is the height of a wave of an ocean base, right? So this is a height. Z denotes a height now. Then this is 1 dimension, 2 dimension, 3 dimension. Then we will get volume, right? Volume of water in the ocean that we're integrating across. I hope these examples gives you some graphical understanding of the meaning of the integral notations. And just like a regular one variable integral, what should you treat other symbols when integrating a multivariable function, right? So what should I do with the y variables when I'm integrating with respect to x, right? We should treat them as a constant, right? Treat all other variable as constant. Right? If the bounds are constant, which it is in this chapter, does the order of integration matter? Right? I think your professor should have told you, right? It does not matter if the bounds are constant, but if the bounds are not constant, then the order of integration does matter. You cannot just change them willy-nilly. You have to do some sort of tricks to convert those bounds, which we will talk about later. Yeah, so let's go ahead and talk about this problem. So let me go ahead and switch back to my notes here. So we have here, and we also have this sheet. So let's go ahead and stack them up together as we always do. So compute the double integral cosine of this, or the R is the region of 0 to pi to 0 to pi. So this, I think everybody can agree, is a double integral for rectangular region problem. Well, I think it's pretty easy to tell because of the double integral notation as well as the dA, right? dA is differential of an area. And so this tells us it's a double integral problem, but more importantly, it's a double integral in rectangular region is because the bound, right? The bound is rectangular. So these are the key words that can tell us that this is the double integral for rectangular region problem. And then I just written down this. Well, this is what I have written down for what we have discussed before, right? Constant bounds for both variables. So to solve this problem, it's pretty straightforward. We're just gonna go ahead and treat all other variables as constant, right? And then work the integrals inside out. So in this case, we're gonna go ahead and set up our problem as just one step. So we're gonna have two integrals, and we have cosine of x plus y, dy dx. I chose this. You can choose dx dy, right? So or dx dy, and then 0 to pi, 0 to pi. So for this region, for this section, we're gonna go ahead and compute the inner part out. Also, I'm gonna go ahead and draw the region of integration for the sake of illustration. So y, x, pi, and pi. Okay, so the inner part is gonna give us sine of x plus y, 0 to pi equals to this is gonna equal to sine x plus pi minus sine of x, and then we can take advantage of the property of sine. This will just become negative sine x. So we're gonna end up with is equals to negative 2 sine x dx, right? We're gonna incorporate the outer integral into our final calculation. So we're gonna have 2 times cosine of x times 2 from 0 to pi, which will give us 2 times negative 1 minus 1 equals to minus 4. So that's all there is for the double integrals in rectangular region, right? So this is the easiest double integral we will be discussing for the rest of the chapter 16. So chapter 16 is going to be all about double integrals as well as triple integrals. So it's pretty straightforward, right? Just notice that this is a constant bound and then set up the integral property and then just go ahead and do it. So that's it for today. Thank you very much for watching. I hope you learned something, and I'll see you guys in the next video.